Hello again. Today we're going to cover Chapter 4, Ratios, Proportions, and Percents. To start off, a ratio is just a comparison of two numbers. For example, 3 to 4. We would write this ratio, right, as a fraction. 3 to 4. We can also write it 3 to 4 and 3 to 4 with a colon in between. So three different ways to write a ratio. We'll be discussing specific types of ratios in a second, but these are the three ways that you need to be familiar with. Right? Most of the time we'll be dealing with a fraction. Right? Very rarely, but sometimes in word problems you'll see it written 3, the word 2, 4. And then if you're working with pitch or gear ratios, you'll usually see it written with a colon, this last option here, 3 to 4. So let's go ahead and take a look at gear ratios. For example, let's say I have two gears. Alright, one gear here with the little teeth all the way around it. Right, this will be our driving gear, and then our driven gear. Right, another gear here again with its little teeth all the way around. We'll call this driving gear, gear A, the driven gear, gear B. Right? What that means, right? The driving gear, it's the one that turns, right? The driven gear B, it's the one that turns because gear A is turning. The gear ratio is the comparison of teeth on the driving gear to the number of teeth on the driven gear. So for example, if there are 64 teeth on the driving gear and 16 teeth on the driven gear, we would write our gear ratio as 64 over 16, always with the driving gear's number of teeth on top, the driven number of gears teeth on bottom. We then want to reduce this fraction, right? 64 over 16. We have a common factor of 16 here. 16 goes into 64 4 times, and 16 goes into 16 once. So 64 over 16, that reduces to 4 over 1. And this then is our gear ratio, 4 to 1. So that means for every 4 teeth on the driving gear, there's 1 tooth on the driven gear. You can also have compression ratio. So for example, in an engine, when the piston is at the bottom of its stroke, there is a cylinder created by that. Alright, the piston down here. And then when the piston is at the top of its stroke, right, there's much less volume right here in the cylinder. So the compression ratio is the comparison between the expanded volume and the compressed volume. So in this case, if the expanded volume is, say, 475 cubic centimeters, or centimeters cubed, right, and the compressed volume is 50 cubic centimeters, or centimeters cubed, right, we would write this compression ratio as 475 over 50. We again reduce this fraction to 19 over 2. However, a compression ratio is usually given as just one number, which means we want to reduce this right to where it's just over 1. So basically we're just going to divide. Numerator divided by denominator, we get 9.5. So again, the compression ratio is just that one number, 9.5, and that of course would be to 1. So 9.5 to 1. We can also have a ratio when talking about the pitch of a roof. If I have here this roof, okay, on top of my little house. So the pitch then is the comparison between the rise and the run, where the rise is this distance from the top of the roof to your ceiling, and then the run then is the distance from the center of the roof out to the edge. So comparison of these two distances, and it's always rise over run. Okay, so in this case, let's say I have a rise of 6 feet, and a run of 48 feet. Right. Then the rise over run would be 6 over 48. I then, of course, reduce this fraction to 1/8, since we have a common factor here of 6. 6 goes into 6 once, and 6 goes into 48 8 times. So our pitch then is 1:8. So these have all been ratios. A ratio can also be used as part of a proportion. A proportion is just a comparison between two ratios. So for example, if I had 3 to 4, and I knew that that was also equal to 9 to 12, this is a proportion, right? The ratio of 3 to 4 is the same as the ratio of 9 to 12. I can prove this with cross multiplication, as we saw in our fractions video when we're comparing sizes of fractions. Here, again, I take 4 times 9, and that gives me 36. 12 times 3, that also gives me 36, which tells me that these two fractions are indeed equal, which makes this proportion true. But what if there is a piece missing in this proportion? Say, for example, I have something to 4 equal to 12 to 16. I want to know, what then do I need to put here to make this proportion true? What is my unknown? I'll call it x in this case. Now I can use the same thing I did here to prove that these two were equal. I'm going to use cross multiplication. Right, 4 times 12, that gives me 48. Then I take 16 times x, and that becomes just 16 times x. I don't know what x is, so that's how I have to leave it. These have to be equal in order for this proportion to be true. Now I'm asking myself, 16 times what is equal to 48? Well, that is the same as asking, what is 48 divided by 16? That, of course, is 3. So that means 12 to 16 is the same as 3 to 4. It does not matter where my unknown is for me to be able to solve my proportion. Say I have some unknown number now in my denominator. 6 to some number is the same as 15 to 10. I can then solve this proportion the same way I did before, again just with cross multiplication. 15 times n, I'm going to say that's 15n, and then that should be equal to 10 times 6, 60. So again, 15 times n equals 60 is the same as saying something is equal to 60 divided by 15. You always divide by whatever number is being multiplied by your unknown. So that number then, n, is equal to 4. Right? 60 divided by 15 is 4. So this proportion then says 15 over 10 is the same as 6 over 4. Those two ratios are the same. So if I gave you the diameter of one pulley, pulley A here, we'll call it 16 inches, and I have another pulley, pulley B, down here, right? Of course these two pulleys will be connected. I do not know the diameter of pulley B, so I'm going to call that x, and I do know the pulley ratio A to B that I want is 8 to 3. So if I know the pulley ratio 8 to 3, and I know the diameter of one of my pulleys, 16 inches, I can then find the size of my other pulley by using a proportion. So I know 8 to 3 has to be the same as the ratio of A to B, 16 to my unknown x. So here, 3 times 16, that gives me 48, and x times 8 gives me 8x. So 8x has to equal 48, or x is the same as 48 divided by 8, which is 6. So that unknown is 6, or in this case, the diameter of my smaller pulley B is 6 inches. So x equals 6 inches. Proportions are used a lot of times in drawings. So for example, say I have this map here. Some river, a little town. The important thing is, on every map there is a scale. For example, 2 inches on this map may be the same as 5 miles. So, if 2 inches is the same as 5 miles, I want to then find out, well, if I measure the length of this, say, river here to be 5 inches, then how many miles does that mean the river actually is along that stretch? I'm then going to compare, right, that ratio, 2 inches to 5 miles, right? That ratio then has to be the same as 5 inches to some number of unknown miles. The key here is to keep inches in the same spot in both of your ratios. So if I have inches to miles in my first ratio, I better have inches to miles in my second ratio for my proportion to be true. I solve this the same way as I have been solving my proportions. Cross multiply. 5 miles times 5 inches. Okay, I get 25. I'm going to ignore my units for now. Right, this has to equal then 2 times x, or 2x. Again, right, what this means is my unknown is equal to the opposite side divided by what I was multiplying by. So 25 over 2 better be equal to my unknown. Or in this case, 25 over 2 is 12.5. So that 5 inches of river along my map is equivalent to, in the real world, 12.5 miles of river. This is also useful in similar figures. So for example, if I have some triangle here, right, a similar figure would be that same shape of a triangle, just smaller. Or again, if I had some large square here, similar figure could be that same shape of the square, just smaller. In order for figures to be similar, they have to have the exact same shape. The only difference is it looks like one is smaller than the other, or one is larger than the other. It can go either way. Right? So the similar figure to this little square is the larger square, and vice versa. The similar figure to this larger square is the smaller square. They don't have to be triangles or squares, they can be any shape. So for example, if I have this odd shape here, as long as the shape is the same, just different size, right, they are similar figures. One place you'll see this in the real world is with shadows. Say for example, you're standing out in the sun, nice bright sunny day. The sun here is going to cast a shadow at a very specific angle. So here's your shadow, and that shadow is going to have a specific distance. Well, everything else is going to create that same triangle when its shadow is cast. Say for example, a flagpole. When the shadow is cast for the flagpole, it has the same angle, thus making it a similar figure to your own shadow. So if you have a tape measure and you know the length of your shadow and your height, say you are 6 feet tall and your shadow is measuring 8 feet, and you know the length of the shadow of the flagpole, say 20 feet, then you can calculate the height of the flagpole. In this case, just by creating your proportion. Again, your height to your shadow's height should be the same as the flagpole's height, which is unknown, to the flagpole shadow's height. So we just solve this proportion and we can calculate the height of the flagpole since we can't reach our tape measure all the way to the top of the flagpole. So 8 times x, we get 8x. 20 times 6, we get 120. So this is the same as our unknown equal to 120 divided by 8, which is 15. So the height of our flagpole then is 15 feet. And we didn't have to pull a Mario, jump on top of the flagpole to find out how tall the flagpole is. These were called direct proportions because as one thing increased, so did the other. So the taller you are, the longer your shadow was going to be. Or the taller the flagpole, the longer your shadow was going to be. However, inverse proportions are just the opposite. Say you're running along, okay? The faster you run, the less time it will take to get you where you're going. So if I run 10 feet here, the faster I run, the shorter time it will take me to get there. Or the slower I run, the longer it will take me to get where I'm going, to cover that same 10 feet. We can see this in a proportion. Say for example, I drove 60 miles per hour for 2 hours. How long then would it take me to go that same distance going 50 miles per hour? I can create my proportion here, now making sure to compare similar measurements. So the miles per hour are going to go on the same side, my 50 to 60. And the difference here with direct proportion is that my measurements that go together are going to be diagonal from each other. So for example, that's 60 miles per hour for 2 hours. The 2 hours will go diagonal from it. And that unknown time will go diagonal from the speed I was going, 50 miles per hour. This is my inverse proportion. Again, inverse because this second ratio has been flipped from what it would have been with a direct proportion. Once we get it set up, it's then just as simple to solve it, cross multiply. 60 times 2, we get 120, and that then has to equal x times 50, or 50x. Our unknown is always equal to the opposite side divided by what's being multiplied by the x. X is 120 divided by 50, or in this case, x is equal to 2 2/5 hours. So what that means, going 60 miles for 2 hours, I can go that same distance going 50 miles per hour for 2 hours and 2/5 of an hour. Let's switch gears here a little bit to percents. So a percent, what that means per cent is of 100. So 1% is the same as 1/100th of something. So if I have this bar here and I cut it up into 100 tiny little slices and I had, say, 40% of it, that means I took 40 of those tiny little pieces out of the 100 pieces that made up that bar. So again, here we see 40% is the same as 40 over 100, 40 of those 100 pieces. That is what a percent means. So I can then convert any percentage into a fraction just by putting it, that 36 here, over 100. So 36% is the same as 36 over 100. 5% then is 5 over 100. If we take this one step further and convert it then to a decimal, 36 over 100, well, that's 36 hundredths, which we saw in our last chapter, is 0.36. 0.36 is 36 hundredths. Or 5 over 100 is 5 hundredths, or 0.05. What we then can see is this pattern, right? 36% is the same as 0.36. That decimal that was right here got moved right here. So if we want to convert a percent to a decimal, say 14%, all we're going to do is take our 14 and move our decimal point 2 places to the left. So 14% is 0.14. Again, that means 2% is 0.02. Again, that decimal place 2 places to the left. 700% then is the same as 7. Again, moving that decimal point 2 places to the left. If I start with a fraction, say for example 1/2, and I want to convert that to a percent, I can first then convert this to a decimal. As we saw in our last video, converting a fraction to a decimal, we take 1 divided by 2, make our decimal point, and our zeros after that. 2 then goes into 10 5 times. 5 times 2 is 10. We have nothing left over, and our decimal point comes straight up. So we see 1/2 is the same as 0.5. 0.5, then if we're converting a decimal to a percent, we're just going to go the opposite direction. Right? Instead of moving our decimal place 2 places to the left, now we move it 2 places to the right. Fill in our extra space here with a 0, and we see 1/2 is equal to 0.5, which is equal to 50%. You can use this same method for any fraction. Convert it to a decimal, and then convert that decimal to a percent. So to recap, if I'm converting a decimal into a percent, say 0.35, I move the decimal place now 2 places to the right to get 35%, and vice versa, going from 35% to a decimal, I move it 2 places to the left. For a fraction, I need to first convert it into a decimal, and then convert that decimal then to a percent. If I'm going the opposite direction, it's actually easier to take that 50%, put it over 100, and then we reduce that fraction. 50 over 100 has a common factor of 50, which reduces to 1 over 2. So if we're going for a percent to a fraction, so 50%, we write that over 100 and then just reduce that fraction. If we're going fraction to percent again, decimal, then percent. Percent problems can actually be solved with a proportion. Most percent questions are actually asked in a sentence like, what is 40% of 50? To solve this, we use the proportion that comes in this type of formula. Is over of equals my percent over 100. The is, that is our what here. Of is we're asking percent of some number. So of 50, 50 will go in our of spot, and then our percent 40 will go in that percent slot. So we see here our unknown over 50 is equal to our percent 40 over 100. And that 100 is always there, it's just part of our formula. We again solve this by cross multiplying. 50 times 40 gives us 2,000. 100 times x gives us 100x. So x then is 2,000 over 100. So x is equal to 20. So that means 20 is 40% of 50. This can also be asked when our percent is unknown. Say for example, we ask 12 is what percent of 48? To solve this again, we plug that into our is over of equals percent over 100 formula. So in this case, 12 over 48 is equal to some unknown percent over 100. Again, solve it the same way with our cross multiplication. 48 times x is 48x. That is equal to then 100 times 12, or 1,200. This then means x is equal to 1,200 over 48, which is equal to 25. So 12 is 25% of 48. So we've seen it asked when we didn't know what our is was. We've also seen it asked when we don't know our percent. What about our of? So say instead I want to ask 30% of what number is 8.7. We see this question is reordered slightly, but we still have our of and our is. This time we don't know our of. We solve it the same way that we've been solving it. 8.7 over our unknown is equal now to 30 over 100. You know, as our percent over 100, our is over our of. Cross multiply to solve. We have 30x equal to 100 times 8.7, 870. Rearrange this as x equals 870 over 30. So x equals 29. So 30% of 29 is 8.7. Let's put this to use. Let's say the weight distribution of a vehicle specifies that the front wheel carries 54% of the weight. If a certain vehicle weighs 3,860 pounds, what weight is carried by the front wheels? And let's round our answer to the nearest pound. To solve this, we want to take a look at the important information. For example, 54% here is important. 3,860 pounds will be important. Let's take a look at what is being done with those. Right? The front wheels are carrying 54% of the weight. The weight is 3,860 pounds. So what weight is being carried by the front wheels? Well, 54% of that weight. Right? We see that as 54% of 3,860 pounds is what? So we have our sentence now that we pulled out of this problem. We convert that to our proportion problem. Is over of is equal to our percent over 100, so 54 over 100. So we cross multiply 100 times x, 100x, and 3,860 times 54, 208,440. So we see x is equal to that 208,440 divided by 100. So x equals 208.40. If we're rounding this to the nearest pound, our nearest pound is right here in the ones place. I take a look at the number to the right. The 4 tells me to round down, so x equals 2,084 pounds. So this then is the weight that can be carried by the front wheels. 54% of 3,860 pounds is about 2,084 pounds. Let's make this a little more complicated then by going shopping. Let's say I have my eye on something that costs $400, but I'm in luck because it is 30% off. So I want to find out how much is it off. Well, that means I'm asking myself 30% of 400 is what? So I have my is, which I don't know, over my of, 400, equals 30 over 100. I calculate my x by cross multiplying. 400 times 30, 12,000 equals 100 times x, 100x. So x then is 12,000 divided by 100, which is equal to 120. So that's $120. That's 30% of my 400. But that's not what I'm going to pay. That's how much the discount was. If I want to find out how much I'm paying, I take my 400 and subtract from it the discount of 120, borrow from my 4, and I get 280. So the $280, that is what I'm going to pay. But now I'm curious, what percentage is this? So I'm paying $280 out of the $400 that it originally was. What percent am I actually paying? Well, I can quickly figure that out knowing that there's only 100% of the total price right here. 30% was taken off, which only leaves 100 minus 30%, or 70%. But let's go ahead and confirm this. Taking my 280 is, right, some percentage, I don't know, of 400, okay, and my percent is over 100. So I calculate this out. 400x equals 28,000. So x equals 28,000 over 400. This gives me 70%. So we see here, right, if I am being discounted 30%, I can calculate that 30%, subtract it from the original price to find out how much I pay, or I can think of it as if 30% is being taken off, then I know 70% is what I'm paying, and all I have to do is calculate 70% of that original price to find how much I pay. So again, here we see two different ways to solve the same problem. Let's switch a little bit to calculate my sales tax. So if I had that $280 purchase, that's what I'm going to be taking my sales tax of, and I have a 9.75% state tax in Arizona and a 2% city tax. That's going to give me a total of 11.75% sales tax. So if I want to find out the sales tax on my $280, I'm asking 11.75% of 280 is what? So that is over of equals my percent over 100. Cross multiply. 280 times 11.75 is 3,290, and 100 times x, 100x. Again, we see x is 3,290 over 100, or 3290. To find my total bill, I take my $280, add to it the sales tax. Okay, again, now adding decimals as we saw in our last chapter. Make sure the decimals are lined up and add. Okay, decimal comes straight down. So I see my total bill is $312.90. I use something very similar to calculate efficiency as well as tolerance. Efficiency is measuring the output, right, compared to my input, and that is going to be some percentage over 100. So if I have an engine rated at 175 horsepower and I'm only getting 140 horsepower out of it, what is the efficiency of that motor? Well, my output is 140, my input 175 in this case. I need to calculate that percentage. Cross multiply. 175x equals 14,000. So x equals 14,000 over 175. So x is equal to 80%. So that has an 80% efficiency. For tolerance over the measurement I'm taking is equal to the percent tolerance, okay, over 100. So if I'm given this measurement, 1.370, give or take, so plus or minus 0.015, the percent tolerance then, right, is my tolerance 0.015 over the measurement 1.370, and that is going to equal then my unknown percent tolerance over 100. Again, we calculate this the same way we've been doing cross multiply. So we have 1.37x equals 1.5. X equals 1.5 over 1.37, or x is equal to 1.0948, so on, or about 1.1%. That is my percent tolerance on this measurement. Right, 1.37 is my measurement, give or take 0.015. The percent tolerance then is 1.1%. The last thing we're going to take a look at is the percent increase and decrease. So to calculate this, we're going to take a look at how much it changed over the original amount. This, of course, is going to give me that percent increase or decrease over 100. So if I have a factory that's pumping out 800 thingamabobs a day, and I have a percent decrease of 8% in production, then how many fewer thingamabobs am I making per day? The unknown amount that changed over the original 800 is equal to that 8% over 100. As usual, cross multiply to solve. We have 100x equals 6,400. So x is the same as 6,400 over 100. So x equals 64. This means that it is producing 64 fewer thingamabobs each day as a result of that 8% decrease. The same goes for increase. If there was an 8% increase, that would tell me that there are 64 more thingamabobs being created each day. So for the decrease, I would subtract the 64 and get 736 thingamabobs being created each day. If I were calculating the increase, I would take that 800 and add the 64, giving me a new total of 864 thingamabobs being created each day. So decrease 736, increase 864. So the difference then is that keyword increase or decrease. This wraps it up for chapter 4. Make sure you took notes, and we will take a closer look at all of this in class. Make sure you print off your homework and bring it in. I will see you guys in class.